We will spend some time this week talking about specific operational practices, but for this module we'll spend some time talking about a little more of the general kind of hodgepodge of different practices and procedures that are important to the operation of a water distribution system. We'll start with system reliability, and we've touched on reliability in the form of the need as an overall objective of the system to maintain adequate pressure and flow. But the reliability of the system is how we make sure that we can maintain that service to our customers. We start with the design of the system. It's really about making sure that we can meet the supply requirements to distribute water to our customers with minimal or no service interruptions. In a system like the El Toro Water District, where all of our drinking water is imported, we have to kind of look at, all right, what happens if we lose our source of supply? And our current goal is that we can withstand at least 60 days of a supply interruption from Metropolitan Water District. It's always challenging, and I've told our board of directors that number used to be 30 days. And we got to 30 days and immediately said, okay, now we need to get to 60 days. So it'll be curious and interesting to see what happens when we say, okay, we can reliably meet 60. Then will it be 90? I'm not quite sure yet. But in any event, how we make sure we can maintain those supply needs. We start with storage and the ability to maintain water for emergencies when our source of supply is not there. We have distribution system tanks, as most systems do, but as I mentioned in the previous module, El Toro Water District also has a very large 275 million gallon reservoir, which is the primary source of emergency supply in the event of a supply interruption for El Toro. Looking at supplies in general, making sure you have redundant sources. So we have water coming from Metropolitan Water District, but very recently, last year as a matter of fact, a new water treatment plant was constructed in southern Orange County, in very close proximity to our district. It was actually a collaborative effort by 5 different agencies serving across different district boundaries, and a wonderful example of 5 agencies coming together regardless of where their boundaries were to meet the best needs of their customers. It was a $100 million new water treatment plant project, but now we get as much as half of our supply at times from that plant. So we've kind of diversified our supply portfolio. It was a $100 million project. It costs more at this point to buy that water from that plant than it does to get it from our previous source, but we called it a reliability premium to make sure we spend a little more money to make sure we can ensure that source of supply. And then there's other options. Agencies that have access to groundwater aren't as reliant as those that have to import water. Having interconnections with other systems so that if your system is down, you can get water from a neighbor is always good. There are water banking projects going on in Southern California where you're maybe storing water hundreds of miles away with the ability to bring it into your system when you need it. Desalination projects are always an interesting animal. There are challenges. They're very costly, more than double the cost of our current import supply. And there are all sorts of environmental issues and really legal issues when the environmentalists initiate litigation to try and prevent some of these plants from being constructed. But there are successfully operating desal plants and others that are on the books. And then there are multiple, and when it comes to source of supply, regional projects become very important with agencies working together to the benefit to the of the common good. Within the distribution system itself, looking at being able to move water back and forth. So if one zone is got an issue, maybe a pump station has failed, maybe a reservoir is out of service for some reason, that you have the ability to move water in a different fashion than normal. Having interconnections within the system so that you have alternative supply zone, maybe at a lower pressure, but with the ability to at least make sure that water is available. Construction standards, making sure that the manner in which the system is constructed is appropriate to ensuring the reliability of the system. It's building new facilities when necessary. It's rehabilitating facilities that are exceeding their useful service life, and it's making sure that you do so in a manner that preserves the operability and reliability of the system. The evaluation, the hydraulic evaluation of the system itself, making sure that the system demands are not exceeding the capacity for which the system was originally designed. As that starts to happen, you impact the ability to maintain adequate pressure and flow and may require upgrades of the system. The potential for power failures always exists. You can never predict when there may be an interruption in the source of power to our facility. So having the ability to bring water in a different fashion, again, it's interconnections, maybe within the distribution system. So you have a pump station that's failed, you can bring water from another zone. Potentially system interconnections, so that you have a problem within your distribution system, but the neighboring city, the neighboring water district, the neighboring private water company, whatever manner in which that system is organized, that you have the ability cooperatively to move water back and forth to benefit either agency that might be in need. And then in reality, in virtually all cases, we have the ability to provide backup power. We have stationary generators at certain water pump stations, so that if power failures, the generator automatically comes on and we don't miss a beat. We get an alarm so that we can respond and figure out what's going on, but the system never stops operating. At other facilities where we don't have stationary generators, we have portable generators that we can tow to the site as soon as we find out, as soon as we get an alarm that there's been a loss of power, and can get the facility back up and running. There are challenges with generators. The Air Quality Management District has specific requirements, so you can't use the generators other than in emergencies, and they've become more expensive as the requirements on emissions for diesel engines have gotten tougher and tougher. But they are an important and critical part of managing the potential for power failures in a water distribution system. And then there's equipment at large that you try to maintain redundancy. Well, maybe it's backhoes, maybe it's other operating equipment that you have the ability to perhaps stage them in different parts of the large system so that it doesn't take a huge amount of time to get them there. Or if something's out of service, you have another piece of equipment that you can use. It's really anticipating what those requirements might be and making sure that you're prepared for a variety of different scenarios. We touched on efficiency as one of the goals of a system operation. Energy management is a big part of it. Pumping consumes a large amount of power. It's probably over 90% of the amount of power that goes into a water system is consumed at pump stations. The State Water Project is the biggest power user in the entire state of California. So the ability to manage that power consumption, because it becomes very expensive. So it's looking at reducing pumping where necessary. It's maximizing the efficiency of the pumps. It's doing proper maintenance on the pumps so they remain as efficient as they can be. It's looking at what the valving is on the pumps so you're not overly eating up pressure that the pumps have to provide. So looking at being as efficient as possible with our pump stations is part of the overall efficiency management for a water distribution system. Optimizing pressure. This is something that translates both into power or into efficiency as well as into leak management. I've had board members ask me, hey, is there something we can do? Can we go with lower pressure that might require less pumping, that might produce less leaks? And in some cases that's possible, but in others that it doesn't work out if you're not being, because again, remember, one of those core objectives is to maintain adequate pressure and flow. And so reducing pressure to save money, you've got that same competing objective, efficiency versus maintaining adequate service. Pipe maintenance, we'll talk a little bit more about when we get into the chapter on pipelines, but it's looking at the possibility of replacing, cleaning, lining water mains if they're not performing at their highest standard anymore. Water loss control is becoming a bigger and bigger issue, especially in California, given the drought conditions that we've been through over the last few years. So you're doing water audits, which basically is an accounting of all the water that enters and leaves the system. So you're trying to make sure that you can track the amount of water that you have brought into the system and that which leaves the system, typically in the form of selling the water to customers. So you typically have meters at the entry points that source of supply, pump stations, wells, whatever they might be, and then are looking at, can we account for all that water? If we brought 10,000 acre feet into the system, did we sell 10,000 acre feet? And to the extent that we didn't, then where did that lost water go? Lost, or what we might say unaccounted for water. Because there are in reality real losses where we've literally lost water, whether it be leaks or something else. And there's apparent losses that are really more about metering, because the truth of the matter is, and we'll talk about this more when we get into meters, meters are a necessary part of a distribution system operation, but they can be suspect. Their accuracy can be suspect. You put 2 meters on the same pipeline, do not expect to get the same result. So some of what appear to be losses can just be metering issues. It used to be that there was an entity called the California Urban Water Conservation Council, and they had a best management practice that suggested if your lost water was more than 10%, then it probably made sense from a dollars and cents standpoint to try and go resolve some of those losses. Typically, we've been fortunate at El Toro Water District. We run at around 3%, which is pretty good. When we look at how much water we bought versus how much we sold, there isn't a big gap. One of the important things, though, is that you do want to meter any internal uses. If you're flushing water, you want to meter that. If you are using water at your own facilities, you want to make sure you meter that so you can account for it. Because ultimately, all of that, when you start looking at those losses, it can help you identify that, hey, maybe we have a leak somewhere. Maybe we have multiple leaks. And there are approaches to go out and try and find leaks that you didn't even know existed. It can be a little bit expensive. So it's a matter of how much water might we save versus how much it might cost to go find it. But the state of California is getting more and more aggressive. They are now requiring that you do water loss audits and submit them to the state, and are really looking at those reports each year and expect to see improvement each year. So it's becoming a much bigger challenge. So talking about O&M practices in general, we'll start with some types of maintenance. We'll identify 2. The first is what we'll call preventive maintenance. This is work that's proactive. It's scheduled maintenance to preserve and extend the useful life of whatever infrastructure might be talking about. So it's things like painting to prevent deterioration, flushing programs to prevent water quality problems that have not yet occurred, scheduled pump maintenance, pipeline replacements that are scheduled, fire hydrant change-out programs, a variety of different programs that we do on a scheduled basis in order to prevent failures from occurring. The opposite is corrective maintenance. Now this is more reactive. Something has already gone wrong. It's unscheduled maintenance that occurs after the appearance of a problem that we have to correct in order to continue operations and to meet our operational objectives. So we're talking about pump stations that have failed. It's kind of the run to fail approach. Mainline breaks, service leaks, things that occur that now we have to react to. And it's far less efficient to deal with that type of repair because we're not prepared. We're prepared in general, but it wasn't scheduled. It wasn't something we planned to do that day. And now we've got to change plans. We've got to stop what we were doing and we got to go to it. So far better to prevent the problems from occurring in the first place oftentimes than to try and react to them. But I want you to understand the difference between the 2 approaches, preventive maintenance versus corrective maintenance. And then there's mainline breaks. We'll talk about those and the difference between scheduled work. And then ultimately, there is no avoiding emergency failures in a water distribution system. They are going to occur, and we need to be prepared to deal with it. So we talk about some of those repair procedures. To begin with, we need to be prepared. We need to be ready to go. We need to anticipate things that can happen, that will happen, and understand and train our staff, make sure we have appropriate resources to respond to those types of unanticipated failures. So one is having an on-call system. We have at any given time 4 people on call at El Toro Water District. One is the primary for pretty much everything that happens. Then we have a supervisor on call to back him up. We have an on-call person for our sewer collection system. We have an on-call person for our wastewater treatment plant. Somebody calls after hours, they leave a message, they get a call back in minutes. Not when we get around to it, but literally within minutes so that we can respond. If we get a call through our SCADA system, through our automatic dialer, then we're responding immediately. So there's an investment there. It costs money just to be, we spend a decent amount of money in overtime, but being prepared to respond quickly is how we maintain that level of service to our customers. I think in one of the discussion forums I read from somebody about a system that you really couldn't get a hold of them after hours and didn't have the ability to get to the system or to get in contact in the event of an emergency. And that's, in my personal opinion, not how we do things. We have a responsibility to our customers. They invest a lot of money in the form of the rates they pay and deserve to have us responsible to make sure we can maintain service to them. It's also making sure we have proper inventory to deal with repairs, spare parts, material on our vehicles that we're able to move quickly, and then also making sure that we have appropriate records and maps so that we understand the system well enough that we know exactly what to do when it comes time to fixing something. The book talks about the first 3 steps. We'll call them repair steps. The first is the ability to isolate the damaged section of pipe. So we've got a mainline leak. Understanding where our valves are and being able to go isolate them so that we can stop the water flow is one of the first things we need to do. It gets challenging, and we'll talk about it when we get to valves, because their valves as they get older don't isolate as well. But with the expectation that we have isolation valves, that's one of the first things that we're going to do. If we're going to be interrupting service, we need to let people know. Sometimes we don't have a choice, that we have to shut the water off before we let them know. That is not ideal by any means. We certainly want to get to them first, tell them, hey, you're about to lose your water service, so give them at least a brief amount of time to prepare for that. But there's other times where we don't have that option, but we need to make sure we're communicating with them as quickly as possible. And then most importantly, contacting Underground Service Alert. It is a law, it is a safety issue, it is a cost issue. There's a variety of reasons why it's critical that we make sure that we don't dig through an electrical line or a gas line, and we'll talk about that in more detail when we get into the module on excavation. When it comes to repairs, safety is a challenge. It can oftentimes be overlooked in the chaos and havoc associated with an emergency repair, but it's something that we can't forget about. We can't forget about the safety of our own staff and making sure that they conduct themselves as they've been trained to ensure that nobody gets hurt. We also have to be concerned about the public, and that means looking at making sure that either pedestrians are handled, traffic control is managed, making sure that all of our staff are using the proper personal protective equipment, especially hard hats, eye protection. We can't use an emergency as an excuse not to properly shore a trench. Anything 5 feet or deeper, we'll talk about that when we get into excavation as well, but anything 5 feet or deeper has to be shored. It is just purely a safety issue. We'll talk about the need to make sure we have proper ladders and stuff like that, but all of the safety requirements that are associated with a scheduled repair are still associated with an emergency repair. There is no excuse for not following all of our safety protocols, regardless of how much of an emergency it might be. Plain and simple. The concept of maintaining positive pressure during repair is an interesting one to me, because for any of you that have actually participated in a mainline repair, maintaining positive pressure means you're continuing to let the water run, which makes for a muddy, if not just exceedingly wet condition that may make the work impossible. So I get the idea. The concept of positive pressure is to reduce the possibility of getting dirty water into the main. If water is coming out, it's not going in. It may reduce the potential for contamination, may reduce the overall need for disinfection, may reduce the possibility that you're draining water out of your customers' lines. But it introduces a significant set of challenges. So it's one that has to be weighed on a case-by-case basis during repairs. So when it comes to the repair itself, oftentimes we're talking about removing and replacing sections of pipe that are failed. It's whether it be, depending on the type of pipe, maybe you're taking it out at the joints, maybe you're cutting it out in between, maybe you're having to weld new steel pipe. It all depends on the pipe material that you're trying to repair, and they come with their own challenges. In some cases, we can avoid the need to, on smaller breaks, and not necessarily, depending on the size of the pipe and the way the pipe is broken, we may be able to go with a repair clamp, which will allow us to put a clamp over the failed portion of the pipe that essentially seals it and will restore the pipe to good working order. And if the repair clamp is properly constructed, and the ones you see here are stainless steel that can last for perhaps as long as the pipe can. It's kind of an individual decision on a system by system and maybe case by case basis as to whether or not this constitutes a permanent repair. I know that our general manager years ago used to tell me that he expected that the repair clamps we put in, that we would go back and replace that section of pipe at some point. And he's still waiting for me to get around to going to replace some of those sections of pipe, because those repair clamps, again, if they are the proper material, can hold on for a good long time. So let's talk about leaks. Some of the factors that lead to pipeline leaks. We'll talk about it when we get into pipeline installation, but the quality of the original installation has a lot to do with how long that pipe will last. Of course, the material, the susceptibility to corrosion, the durability of the material, the strength of the pipeline can have a lot to do whether or not it's prone to leaks. As would be expected, the age of a system. The older the pipe, the more likely you can have leaks. Now, in reality, pipeline useful lives can range from 50 to exceeding 100 years. So if the pipe is properly installed and properly maintained, you should get a long life out of it. I touched on it earlier, but higher pressure means more potential for leaks. The pipelines we use in this day and age are capable of withstanding very high pressures, but it is kind of intuitively obvious that the higher the pressure, the more potential for leaks. And then you have local factors like traffic loads, arterial streets with more traffic loads on the pipe, depending on how well it was installed and what the backfill was like. Soil movement, especially in Southern California, can also contribute to leaks in main lines. One of the things we try to evaluate is it an emergency or not an emergency? So what's going to drive something to be an emergency where we have to roll right now and get it repaired as quickly as possible? Typically, a mainline leak is likely going to be an emergency because of the amount of water you're discharging, the potential for hazards that it's going to create in the street, and the collateral damage to streets and buildings. Non-emergencies are typically going to be things like service lines, maybe you got a valve that's not working properly, or in some cases some smaller main lines where you have the ability to manage the leak while you more proactively plan the repair. But in some cases, those leaks may not surface real quickly. You've seen them in many cases where the leak, in fact, we've had to dig multiple holes trying to figure out, all right, we know we have a leak, but we can't seem to find it. So that is something that ends up being more of a scheduled repair. The impacts of leaks, the big issue aside from the significant loss of water is the potential for damage to property, personal injury, especially in a street where you can impact traffic and can have significant injury if a car gets in there. You have the potential for contamination of the system anytime you have a leak. Further cave-ins that exacerbate the area of the damage. And of course the cost. Anytime you have a leak, you're losing water, which costs money in and of itself, but the cost of the repair can be extensive. Leak detection is the simplest way typically that we know we have a leak is we see water underground. We see either just a wet spot or we see water running down the street. In some cases we see significant changes in metering that tells us, wait a minute, where's all this water going? If we know we have leaks some places, we're trying to go figure it out. There are sonic leak detectors that can locate leaks. It becomes a bit of a challenge, though. The best way is where we can see water in the ground. Other than that, it becomes a pretty significant effort. And then, of course, as we've touched on several times, anytime we have a leak, we are losing water. And in the resource-challenged California, when it comes to water, every bit of water that we can't put to productive use that we lose is a problem. So we try to operate the systems in a manner to mitigate and reduce as much as possible the amount of water that we don't actually ultimately get to benefit from. Locating pipes is another important part of, or the ability to locate pipes is another important part of the operation of a water distribution system. So we start with having good records. That's maps. It's maps available to our operators that are updated and kept current, making sure that when we have construction, that we have good record drawings. That is kind of normal practice in this day and age. The record drawings from projects that were installed many years ago is a little more challenging, especially as the surrounding areas have changed, and it becomes difficult sometimes to find some of those pipelines that we don't have as good a records on, and so we've got to employ different options to try and find them. In some cases, we can use metal detectors, but in reality, they're not going to help us much with pipeline location, although they can help us find valve cans that might have been buried during a street resurfacing project or even manholes. For metallic pipe, electronic locators can help out, whether it be through a radio transmission unit like the one you see here, where we are essentially applying an electromagnetic field and the above ground receiver can locate it and we can trace the pipe, but really only works for metallic pipelines. There is ground probing radar that's a newer technology, but gets a bit expensive. When it comes to trying to find non-metallic pipes, now we've got some more challenges. If it's a new pipeline that we're installing today, we are going to put in tracer wire. And you see that little blue wire in this picture, and we've installed well over 100,000 feet of recycled water pipeline recently, the vast majority of which was PVC pipe. So you can't trace it with electronic locator, but every bit of it went in with this wire. So if we ever can't find one of these pipes, we connect to the wire, we can trace it electronically, we'll know exactly where it is. However, as I said, lots of older pipelines don't benefit from stuff like this. So there is, and everybody probably knows, somebody who has the skill and ability to use these dowsing rods, or as our staff used to call them, witching sticks. I refer to it simply as black magic. But if anybody's ever seen someone who's skilled at doing this, it is amazing to me how often it works, where they're simply with what looks like a couple bent coat hangers in their hand, they can walk across the ground and suddenly point down and say the pipeline's right here. And we had a guy who more often than, well, not more often than not, almost always was absolutely right. That pipe was within at least a couple feet of where he said it was. So I've heard a lot of different theories on why it works. I've seen it work. I would much prefer to have the ability to electronically locate a pipe or verify it with very good record drawings. But as a last resort, this is, you do what you got to do.